Welcome PCS members and friends to our today's PCS IBS seminar. It is a great pleasure to have with us today Mr. Paul Schindler from MPI PKS in Dresden, Germany. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Yeah, thanks, Dylan. So let me repeat what Dylan has already said. We have today with us Paul Schindler. He's going to talk about the variational ansatz for the ground state of the Quantum Sherrington-Kirkpatrick model. So Paul is currently a PhD student at the Max Planck Institute for Physics of Complex Systems in Dresden, which many of us know. And with this, Paul, please, the screen is all yours. You can start.
Thank you very much for the introduction and invitation to talk. So first of all, please, if there's some questions or if you don't understand something, speak up and interrupt me at any point. And yeah, so this is some work I've done during my master's in Munich at the Max Planck Institute for quantum optics, in collaboration with Tommaso Guaita, who is now in Berlin, Tao Shi from Beijing, Eugene Lemler at ETH Zurich, and of course supervised by Ignacio Sirac at MPQ. And yeah, as the name suggests, we have two main parts that I will going to talk about in my introduction, which is first the Quantum Sherrington-Kirkpatrick model. I give you some introduction what this model is and why it might be interesting. And then I will introduce you some the ansatz that we are using to study this model. So the Quantum Sherrington-Kirkpatrick model is basically some infinite range mixed field Ising model, which has quenched this order. So let's make this a bit more slowly. So I have written down here the Hamiltonian. It's a spin-1/2 system, and we have some all-to-all coupling, some Ising type coupling, where we have here some random parameters. Then we have a homogeneous transverse field and some random longitudinal field. And these random fields, so these random variables are Gaussian distributed and identically independently distributed. And so first of all, this all-to-all coupling is usually a bit difficult to imagine. So I draw this little sketch to just show you how counterintuitive this is a bit, because since we have this all-to-all coupling, which is random with mean 0 and some finite variance, we first of all have ferromagnetic and antiferromagnetic couplings, and we basically have no notion of geometry really. So this is you get the closest to it if you think about this as being some infinite dimensional model, because everything is connected to everything. So we have maximal connected system. This model is famous in if you cross out this transverse field, because then it reduces to the classical Sherrington-Kirkpatrick model. So we have a fully classical model, which is one of the best examples of a spin class model, and a fully solvable one, which was solved by Giorgio Parisi some while ago by the famous replica symmetry breaking, which gave him the Nobel Prize, I think, 2 years ago. And so it's so this classical model is well known to describe spin classes, and so it has some correlations with or some interactions between this order and these antiferromagnetic couplings, all-to-all couplings. And if we introduce quantum mechanics by this transverse field, we get a very interesting model, because on top of this frustration and statistical fluctuations, we also introduce some quantum fluctuations, where a lot of interesting questions arise. And on top of this, despite this model looking like it cannot be realized in a lab due to this long-range interactions, it's actually realizable in a system where you have atoms and photons, as shown here in this paper when you integrate also photons. This model is very interesting in many perspectives, but we will focus on ground states and equilibrium. And this has a very rich phase diagram, which I sketched on the right. So first of all, as already indicated, in the absence of a transverse field, so in a fully classical case, this model was fully solved by Parisi, but already sometime before, Almeida and Taulis have indicated that there will be a entire line of phase transitions, the so-called AT or Almeida-Taulis line, where the system goes from a disordered paramagnet to an ordered spin class phase. And while you have this exact solution in some sense in the classical domain, once we introduce the transverse field, so once we enter the quantum regime, there are no exact solutions known. Yet, especially in the absence of this longitudinal field, so if we consider only the TEG plane, this model has been extensively studied by means of numerical methods like quantum Monte Carlo, but also exact diagonalization methods, and also more analytically approximate methods like replica tricks, like the replica trick in field theory. But yeah, as said, there's no exact solution. And it's also somewhat debated when we reach zero temperature for a lot of things, like whether there is replica symmetry breaking or not, and in which regimes we find this. But also there is the proposed quantum Almeida-Taulis line, so a line of phase transitions, basically in the plane of longitudinal and transverse field, which is debated to exist. So it was proposed, I think, 2017 by Young. Since this model has been so scarcely studied, and in the zero temperature domain, mainly because ED methods cannot go to large system sizes, but we suffer actually from strong finite size effects. And all these other methods usually need some extrapolation to zero temperature. We thought that we might go a different direction and start at a method which is very suitable for zero temperature, which are some variational ansatz. So our variational ansatz is called generalized atomic coherent state. So let me first introduce what atomic coherent state is. So basically, it's a fancy name for product states, for spin 1/2 product states. So you just have a system of n spins, and each of the spins lives on a Bloch sphere, basically independent of the other ones. There are no correlations between the spins. You can nicely write this product state as picking one side where everything points up and then rotating each of the spins individually by some sv2 rotation. This is a computationally very efficient ansatz, but it also lacks a lot of things like correlations, for example. So we don't expect this to perform well. So what we did is we used a method which is a bit more expressive by introducing some additional correlations in the sense of this generalized atomic coherent states, where on top of this atomic coherent state, you introduce some entangling gate, and then you rotate again. This entangling gate is basically some CC term between any two spins. We have this weight matrix M over here, so it's a symmetric weight matrix, which describes how much two spins are entangled by this Ising term. The final rotation ensures that this picking CC is nothing special. And in this case, on the right-hand side, all the sort of variation parameters are the x, y, and m. So we have basically n squared parameters, and on the left side, which we also use later for comparison, we have basically linearly many parameters. So why are we using this ansatz?
Paul,
yeah?
we have a question from Alex.
Sure, go ahead.
Yeah, is this generalized atomic coherent states, is it related to in any way to the restricted Boltzmann machine?
Well, I'm not an expert in the restricted Boltzmann machine. I cannot answer so it could be that there's some relation, but I'm not entirely certain on how. So if either of them includes the other or not, or whether they are going further, because I don't quite see how these hidden variables could produce this term.
Well,
yes.
Yeah, I'm not sure. It doesn't look exactly the same, because in the restricted Boltzmann machine you would not have a product, but somehow it seems to me that it can also capture the correlations that they can capture with this ansatz. But this is just a hunch.
Yeah, it's interesting. Question. Yeah, I would need to look it up and see how they related.
Thanks.
Yeah, thank you for the question. Yeah, where was yeah, for variation ansatz to be good, it does it's not only need to be expressive, because then we can use the full Hilbert space. It should also be computationally efficient, and we reach this due to this nice identity. So what we need to calculate usually are expectation values of some observables, and they will always have this sandwich here where we have this V dagger, then some Pauli operator, and then some V. And this boils down to some product of operators, which is very simple, and so computationally very efficient. Though we still have these correlations in there, because the Pauli operator on the nth side, or the expectation value of this operator, now depends on all other sides. Yes, and there's some, so what I don't know whether they are related to this restricted Boltzmann machines. I know that these states are also known in literature as weighted graph states, because you can draw this very simple picture when you use this language. So the state is basically built out of starting with this coherent state, where you take each spin and rotate it into the direction, and then you basically take your spins as some graph, and where these points correspond to the spins, and the links correspond to the weight or the correlation between the spins, and then you apply some kind of rotation, which gives us a very intuitive picture, I think, what is happening. Yeah, so now I've introduced some sites to you, and so the question is, how well do they perform? So the next part, I want to convince you that they capture some essential physics of the Quantum Sherrington-Kirkpatrick model. So for most of the talk, I will restrict myself to the simplified model, where we throw out all the longitudinal field, and only if some time is left in the end, I will reintroduce this field and talk about this, whether we find signatures of this quantum AT line. But if we now look at the energy, which is so that the variational ground state energy, which is, I think, a very good measure to see how good your variation ansatz is. I mean, this is a native measure in some sense. Then we see two things in the beginning. So we just plotted the energy of the ground states for these atomic coherent states, the generalized atomic coherent states, and some numerically exact results. And if you just look at the energy, you will see almost nothing. So this purple AD basically lies perfectly on GCS, and you see some small deviation for the coherent states. But we can already see that we're actually quite close in absolute measures to this energy. So let's look at the difference between the variational ones and the exact one. And yeah, as I said before, so I mean, we are very close to the exact ones already. But importantly, we see that our Forest Ansatz performs much better than the simple product side. So we will definitely see an improvement upon this Ansatz, and we also see that where we see some bump which shifts to larger transverse field values, we don't really see an increase. Actually, we see a decrease in the error, and it's also expected that this transverse field, at the maximum moves with increasing transverse field values, because also if you look at phase transition point for the system, then this will lie around these points for this finite size system, and it's expected that there the deviation between the exact result and our variational one is the strongest.
We have another question from Alexei.
Sure.
Yeah, so these curves, are they the average ones?
Yeah. Thank you very much. Everything which I show you is always averaged over the disorder. Yes. Very important question. Yeah. So I usually take 1,000 samples and average over these samples, and so I tested this, of course. So for 500, it's basically converged, and then I took twice as many. And also the error bars are smaller than the symbols shown here.
Oh, okay. That was basically, I think, more or less my next question, because I was curious, if you look at the individual samples, to compare the energies given by exact diagonalization and the Ansatz, then how would they compare?
Yeah, it's basically the same. So if you look at the so you would of course find samples which are better and worse, especially throughout basically. But if you look at the confidence interval, like the 99% confidence interval of these averaged data, then the error bars would be smaller than the symbols. Yes.
Okay. Thanks.
Yeah. Thank you very much. So actually, in everything which follows, it's always averaged, and if there are no error bars, then the error bars will be always smaller than the symbols.
We also have a question, yes, from Dario.
Yeah, a simple question. I mean, I'm not sure I can formulate properly, but more or less the question is as follows. I mean, in this improvement, is it possible to understand how much the contribution of this improvement is coming from the fact that you are adding correlation with respect to the fact that you are just adding more parameters? I mean, in the GCS, there are many more parameters that you can tune. So I'm wondering if you can distinguish, let's say, the improvement which is genuinely given because the GCS with respect to the CS has correlations, with the improvement which is just due to the fact that you have many more parameters to tune.
Yeah, because so actually we don't have so many more parameters. Of course, we have these. Let me go here. We have these n squared more, but they only introduce correlations because the outer rotation would be trivial if the weight matrix is trivial, because then it's just two rotations and you can combine it into one. So there's actually not so much that we are better.
I see.
So we have introduced so much. Yeah.
Okay. Thanks.
Does this answer your question?
Yes.
Okay. Thank you. All right. Yeah. Here, I show basically the same thing again. So there's the scaling of these of this maximum here and where at which point it occurs. But I mean, you already see the issue. We cannot go so far. Of course, we could go to 20 spins with ED, and then we see basically not so much change. But yeah, we cannot go very far with exact methods. But of course, with these variation methods, we can go much further, and we can at least test whether this enormous improvement here can also be seen for much larger system sizes. And so what we've done, we compared the CS and the GCS one scaled by the system size, and these curves show a very nice saturation when we go to 200 spins. So from 100 to 200, there's basically no change. So we have an extensive improvement in energy, at least compared to the simple product states. And yeah, this is basically all we can cite, because ED doesn't really work after 20 spins. But so this is basically the regime of small system sizes. But of course, this model has been studied considering its phases. And so we can look at the phase transition, which is more something at infinite system size. And in order to study this phase transition, we look at this spin class substitutability, which is basically the CC correlation squared and then averaged. So the squared is averaged. So this over bar indicates the disorder average. Yeah, I mean, first of all, comparing this again to ED1, so the same system sizes, we see some qualitative, we see some quite good agreement quantitatively, and we also see that it decreases in system size, but the system sizes are just not big enough so that we can say where it converges to. Yeah, but
we have another question from
Go ahead, please.
Yeah, sorry, can you go to the previous slide?
Sure. So there you go.
Now, how we compute the energy at such large system sizes? I mean, I understand that you cannot do exact diagonalization, of course, because it's too large. But even how to compute the energy, I may be.
For our variation ansatz, it's quite simple, because you can basically this this equation I wrote down over here, like this one. Oh, sorry. This thing allows us to write down some semi-analytical equation, which then only scales quadratically in the system size.
I see. Okay, thanks.
Yeah.
Okay, good, thanks.
Okay. And this is for all expectation values. We can basically we can calculate all expectation values in scaling more or less quadratically.
Okay, thanks.
Yes. Yeah, and as I said, so we can go to much larger system sizes now and look at this phase transition and this order parameter. And so this is the extensive definition, and the intensive one is just divided by the system size. Should in the paramagnetic phase, it has an order parameter in the thermodynamic limits at 0. When it's 0, we are in the disorder phase, and it attains some finite value in the spin class phase. And first of all, so blue is again the GCS and red is the CS. We see that both show indications of a phase transition. We have a spin class regime in both cases and some paramagnetic regime. And we also see that they are basically converged. If we double the system size, there's hardly any difference in where the critical point is. But we see that the critical point is very different. And whereas the CS have some critical point around 2, the GC is actually very close to the critical point, also known in the literature, which lies around 1.5, 1.6-ish. So this gives us confidence. So not only this parameter, there are also others that we tested. And this is always what we see. This gives us confidence that at least in the thermodynamic limit, we're well capable of capturing essential physics of the phase transition. And that the correlations are essential in capturing this, because we clearly see that the CS underestimate the quantum fluctuations. All right, so with this, we are quite confident that we have a good ansatz which describes some, at least qualitative physics of the model very well, and to some extent also quantitative. So we want to do also something new, and using a variational ansatz, having really a state, gives us a unique toolbox which is not achievable, for example, with quantum Monte Carlo, or at least not easily, and also not with the field theory methods. And which is that we can also study entanglement entropy. In particular, I will look at Rényi 2 entropy, which is defined as follows. So this is the log of the trace of the reduced density matrix squared, where the reduced density matrix is we take our system and divide it into small pieces, a system, subsystem A, and some complement of this. Trace out the complement. And the nice thing is that we can rewrite this as some expectation value, introducing the swap operator, where we basically double our system and then swap the respective systems. And we can rewrite this even further, as was shown in the paper in the appendix, into some Monte Carlo method. So we can calculate this expectation value using some simple Monte Carlo technique, just from the form of the equations that we find of some effective spin 1 system, which is not frustrated or anything. So we can very easily calculate this Rényi entropy. Actually, it's much easier to calculate this Rényi entropy for a given state than finding the effective ground state, the variation ground state.
We have another question from Alex.
Yeah, go ahead.
Sorry, the question is related to the previous slide where you showed the large system sizes. Did I miss it, or did you try to estimate the transition point from your variational results? So what I've done is I tried to so I used various methods. So I also tried some finite size scaling, but actually these results are so well converged that you can literally read it off by looking at these values. And so it's between 1.5 and 1.6. The thing is just that I haven't looked like very deeply, so I haven't scanned through this in much resolution, so I cannot perfectly say where it lies. It also varies a bit with the method I use. So mostly I find something which is around 1.545. 1.545. Okay, which I think is pretty close indeed to the other estimates. Also, actually, it was quite hard to find a perfect agreement, because there's some. I think the literature is also not entirely certain where it exactly lies. It depends a bit on the method, whether it's around 1.5 or 1.6. Okay, thanks.
All right. Yes, but so first of all, before I show you the entanglement results, I want to set them into some context and show you why they have surprised us. Actually, we have already been surprised by the fact that the GCS performed so much better, because we had the following intuition, which eventually turns out not to be the perfect one, but it seemed to be a very valid one. So if you take a closer look at this model, it's an all-to-all connected model. So of course, due to this randomness here, we are not permutation invariant. But if you look at on the level of this order averages, we will find so once you averaged over this, it doesn't matter at which spin you look. Everything should be the same for each spin. So we have permutation invariance. So one might think that one can also find the correct result by using a permutation invariant state and basically finding a suitable parent Hamiltonian fold, which effectively describes this model. But the thing is, if you have a permutation invariant state, then you can always also write down a Schmidt decomposition, where you decompose into subsystem A and the complement, such that this subsystem states are again permutationally invariant, and also in the complement of permutation invariant. But actually, there are not so many of such states. For a subsystem of size L, there are only L plus one many of these permutation invariant states, which, if you plug everything into the equation for the Rayleigh entropy, leads to a logarithmic scaling of the Rayleigh entropy if you consider large subsystem sizes. Of course, large subsystem sizes, which are still much smaller than the entire system size. And this is why we've been surprised that we have so many correlations, because we thought that, well, actually, we have a long range, so we have an infinite range interacting system. So if one spin shares correlations with another spin, and this is permutationally invariant, it should share the same correlation with all spins. But actually, you will see that's not the case. So what I've plotted here is now the Rayleigh entropy for different system sizes. So the maximum value is the system size up to 200 system sizes. And we see and it's of course averaged. We see the standard structure. So we have the symmetry around half of the system size, which is important. So why it's important to have a large system size, because you usually are interested in the regime where this system size L, the subsystem size L, is much larger than 1 to extract basically a scaling in the Fermat limit, but it must be much smaller than half of the system size in order that we don't touch this turning point. To extract the scaling, we looked at this phenomenological ansatz, which is usually used, and fitted it to our curves. These are the red lines that you can see here. And from this, you can nicely get the scaling by fitting these A's and B's, and looking at at how they behave for large system sizes. And this I will quickly try to write down. Because the thing is, if we take this S2 bar and look at limit of L being much smaller than entire system size, and then we can of course expand the sign. So Taylor expanded into first order, then we get something which is an log 1 plus b of n, then L divided by n. And now it depends strongly on what these parameters are. So for example, if b over n goes to some constant value as the system size increases, then we can get some logarithmic scaling. But if this goes to 0, then we can again expand the logarithm, and we will then get something which potentially scales as a volume law in the system size. And indeed, so we call this parameter C. We find the later case, as I will show you in a second. Yeah. So if we plot this coefficient as a function of the transverse field, and for different system sizes, we first of all see that it converges in system size. So we have indeed this scaling that, so we have also of course looked at B over N, and it decreases, but the entire coefficient here takes a finite value. So we have a volume law scaling, what is called volume law scaling, and not a logarithmic scaling in the Renyi entropy, which in itself is, for us at least, a very surprising result. And what's even more interesting is that at each point of this phase diagram, we have a volume law scaling. Only the coefficient in front of it basically is different. And this coefficient also has this cusp structure at 1.5. So we have this non-analyticity which emerges for increasing system size around the transition point. So also this the entropy can be used at least as a witness for the phase transition. Which was turned out to be very interesting. So why? So we wondered what is happening. So we looked again at the sites, and the important part, which introduces the correlations, which also goes a little back to the other question, is this weight matrix here. So we took a closer look at it. So first of all, here on the left, upper left, I just took one realization and looked at it and saw that it looks a bit like a mess. And then before there, let's maybe look at the distribution. So we took, so I mean, this is obviously for 100 spins. And then we took our 1,000 samples for this 100 spins and looked at the distribution of these M values. And notice this is a log ln scale. And we find very, very good agreement with this black curve, which is an exponential. So it seems that our M's are normally distributed, just as our interactions are. And we also see that if we look at the width of this distribution, that it decays as 1 over n. So if we make a very, very simple argument, where we again look at this graph thing here, and we look at the links or the correlations we can have, or which contribute to Renyi entropy, then we see that, of course, only those correlations which connect spins from the subsystem A to its complement are those which can contribute. All others are traced out. And there are L times n minus L many links. And we know that each contribution of them, so the entropy per link, scales as 1 over n. So if you take the large system size, then we find again this volume law scaling. And we actually can make this a bit more rigorous. This is also shown in the appendix, or I could talk about later. But we also tested this numerically by using these the simplest form of weighted graph states, where we just take a trivial product state, which is all X magnetized, and apply a matrix on them, which is so where we take these weights to be just normally distributed with variance 1 over n, and then basically average over these weights. And we find the very same functional form as we find for the ground state of the Quantum Sherrington-Kirkpatrick model, which suggests that at least the correlation structure is already given by this simple form. But of course, this is the true structure also needs these subsystems, so there's more in it in the Quantum Sherrington-Kirkpatrick model, as we can also see by this non-trivial relation for the coefficient.
Paul, we have a question from Alexei.
Yeah.
Yeah. Again, previous slide, please.
Yeah.
Yeah. So, did you check for possible correlations? I mean, you found that the individual elements are Gaussian distributed. Mm-hmm. Are there any correlations, or they're well approximated by independent Gaussian variables?
Yeah. We see that the correlations go down, I think, as 1 over n squared. So there are some correlations, and if we at least for the finite amount of samples that we have, but we see that they decay faster than this variance. So, I mean, in a higher polynomial. Yeah. Yeah. Thank you very much for this question. Okay, I think I have some time left. Then I would also touch on this other part, which is this finite longitudinal field, and to say what our variational ansatz gives. So first of all, this and other results, when they proposed showed evidence against this transition, usually use some field theory methods which rely on the existence or absence of replica symmetry breaking. And this is not the case for our ansatz. Of course, it has its own difficulties, but it's at least not biased in the sense that we need or don't need replica symmetry. Yes, so the question is, can we also find this transition line? And indeed, if we look at our results for different longitudinal fields at different entities which are witnesses of the phase transition, then we always find that this sharp non-analyticity basically gets smeared out once we introduce any form of longitudinal field. So we, so any transition structure is always smeared out. We can find this very dominantly in this correlation coefficient that I showed you before, where we have this very dominant peak. So the data is here all for 200 spins. And then the color indicates the strength of the longitudinal field, with black being the strongest, the weakest field 0, and then to some strong field. And we have a very dominant peak where we don't have a longitudinal field, but as soon as we turn it on, it smears out and gets less dominant. The same is also in the order parameter. We have this very dominant, basically transition from being linear to being 0 usually, which then gets smeared out into some smooth results. So at least we cannot find any signature of this phase transition, which in itself shows it. This should be studied in more detail. We find more of, please don't be too harsh on the words. We find something which looks more like what you usually see in some quantum critical regime. So we still see these bumps, but they are always smeared out. So the introduction of longitudinal field, at least in our case for our method, seems to totally destroy this transition. All right. With this, let me summarize. So we introduce a computationally very efficient ansatz, which extends this atomic coherent state, and which can also have a very rich entanglement structure. What I haven't shown you is that we can actually, so it's not generic that the states always have a volume law scaling. You could actually choose the weight matrices so that you get any sort of scaling logarithmically, of course 0, because the current states always have 0, up to volume law. And then we have found that the GCS are very well captured small system size, but also the phase transition of the quantum Sherrington-Kirkpatrick model, at least in a regime which is well studied. And we have seen that these ground states, variational ground states, candidates for the quantum Sherrington-Kirkpatrick model show a non-trivial volume law entanglement, which has not been studied before. But of course, there are a lot of open questions. So first of all, we introduced actually a quite versatile ansatz, which could also be used in other cases for other long-range models. Then we have barely touched the variational toolbox. Of course, one could do some TDVP, and also further extend the ansatz, especially if you look at some non-infinite range models or some other long-range models. Then it might be that, for example, this new entangling structure or this additional entangling structure that we used might be able to capture the long-range terms, and you could, for example, imagine to support this by some matrix product state to capture better the short-range correlations. Okay, with this I want to conclude, and I'm open for more questions.
Thank you, Paul, for this excellent presentation. Let us thank our speaker. And we have time for questions. Dario, I see, has a question.
Yeah, a bit unrelated, probably to the model that you studied today. This is more related to this ansatz. This ansatz is suitable for I mean, to be implemented on real, let's say, quantum computers. I mean, is an ansatz that is friendly for being implemented on a quantum machine?
Yeah, actually, if you take a close look at it, you see that it's can I see it again? There you go. It's actually a one-layer QAOA. If you wish. So yes.
Have you tried to or are you interested in trying to make it to implement it on some quantum computer and see how it
basically, yes. So what we thought about is so of course it would be interesting to look at it from the QAA perspective, but it might also be interesting to basically pre-train this one layer, and then add a second layer on top of it, which is then not analytically optimizable, but on a quantum computer optimizable. I think this would be interesting to see whether this can maybe circumvent the issues you usually have with QAOAs on quantum computers and finding local minima and all of these things.
I see. Okay, yeah, thanks.
Can I ask maybe you mentioned excuse me, you mentioned an experimental setup. So is there any lab that you are aware of that is trying to see any of these?
So this is a good question. So when I started this, actually, I think Ben Leff was sort of interested in trying this, but this is now over a year ago, so I don't know what the current state is. So I think there was some, what was it? Yeah, there were some clues around also this proposal, because you can implement this with cavities in principle, but yeah, I don't know what the current state is.
Okay, thank you. We also have a question from Alexei.
Okay, yeah, this is a bit related to you mentioning the other long-range models. Do you think this has chances to work well on things like random regular graphs? So this, or like beta lattice, this is something that is still, let's say, min field. So you expect many of the features to carry over, but you get some notion of a distance. So
yeah, truth be told, I don't know. I can, yeah, I'm not really an expert on these models. It might be worth a try. Yeah, because there you could also nicely compare to beta ansatz. Yeah, but I don't know. I think I mean they perform, I think, always well when the main difficulty of the ground set is that the correlations are long range, but of course the correlations that we introduce are extremely simple in some sense. So taking them and you know, if you expect a highly non-trivial correlation structure, then this might not be the best ansatz, or at least not in its current version.
Okay, yeah, but you mentioned that basically you might, I mean, at least one idea is to combine these ansatz with the matrix product states, exactly to address short-range correlation matrix product states and long-range ones with. So that potentially might do the job on the. Right, and yeah, another question that's again. Well, actually, have you tried this ansatz? Does it even work for the classical model?
The thing is, if you drop
the quantum, the transverse field.
I mean so this is a very excellent question, which goes into some difficulties and how we, or let's say some procedure on how we actually obtain all of these results. The thing is that we always include here this zero transverse field. And of course, as with all variation methods, you can always run into some local minima. And in fact, this is what usually happens. So if you, I mean, at zero transverse fields, we have a classical state. So we don't even need the GCS. Everything is captured by product states. And if you look at this point and just optimize with product states, you will find a lot of local minima up to some finite. Let me show you the other thing here. Up to some finite region of transverse field value, which is notably smaller than the transition point. And so what we do is we make it a bit brute force. We look at this point at 0 and I mean, the CS are extremely efficient, so we could go up to 10,000 spins. But what we do instead, we look at some given system size and initialize some random state and then make the optimization procedure to find the local minimum again and again and again and again for 100,000 times. And then we look at what is the state which has the smallest value and see whether or like how often it occurred. And we looked at some distributions on how much we find. And we take this state, which we are rather confident about that it's a good state, and use it as the ansatz for the next higher transverse field value. And by this, so basically adiabatically go from some low transverse field value to some high transverse field value. And we compare this, of course, to just looking at one point and taking a lot of samples, basically, and we find that it always performed better than all other methods that we would come up. So
okay, so you do.
Yeah.
No, go on.
No, just no. That's it. So we are quite confident that we capture, or that we are at least very, very close to the optimal minimum at zero transverse field value, at least for the system sizes that we consider.
Okay, so you do have this problem of multiple local minima for small enough transverse fields. Because my question was, among the other long-range models, I was curious if this ansatz might capture, say, instead of the Sherrington-Kirkpatrick, you go to the vector Sherrington-Kirkpatrick. So you allow spins not to be Ising, but Y or vector. Because I think that model hasn't been, I mean, there are some predictions, but I'm not aware of any solutions. Although there, you have, at least for the classical case, you have, you could just align spins with the local fields, and that also generates a lot of local minima. And I wonder how that would compare to your construction.
Yeah, that's actually a good question. So yeah, this would definitely be something worth looking into. Yeah, because just yes, as well, I don't know, and would be interesting to look into.
Okay, thanks.
Okay, do we have any other questions from the audience? It seems not. So in this case, let us thank Paul again. And thank you all for coming. With this, we